Yeah.
Oh, if there's something that you specifically, like, I mean, so I cover more stuff here than, like in the lecture notes, I cover more material than are the core. I mean, these are the core ideas. Like, if you understand each of these, you're fine. There's a lot of details in terms of parameter estimation. I'm just saying, if you want to ask, are we responsible for blah? I'll answer as long as you don't, like, are we responsible for multivariate, you know, I mean, you could eventually decode it into literally getting the exam out of me, so. I'm just saying.
So we only have, what, 3 hours?
Yeah, right. I know, I'm just saying. Any questions fair? I'll just tell you if I can answer. So search I did on the board, but I'm not going to cover search. I mean, you should know about search and length in general, but I'm not going to ask any direct search questions. Like, I talked a little bit about like, admissibility and consistency and some things like that. They're not relevant. Okay. So again, this is just feature engineering type stuff. The important thing here is these were all discrete, so the idea was it was suitable for doing decision trees. Discrete features are very easy to do decision trees with. We also do eventually extend it to real value cases. So this was our tennis example, where we had all either categorical or binary variables. So I guess the only thing really relevant here is, as I already said, any decision tree can learn any logical function. So when you have all discrete variables, as long as your data is noise-free, there is a consistent decision tree that exists. And what our goal, as far as machine learning goes, because you can come up with an algorithm that does it in a naive way, is to come up with an algorithm that makes compact trees. Because compactness, we believe, generalizes better under this Occam's razor idea. And as I said, trees to rules, so knowing that trees can go to rules, it's very easy to see I can write trees in the dumbest way possible. You just start with the leaf and basically take conjunctions down and multiplies. Yeah?
So you had said that you can have a consistent tree if you have noise-free data.
Yeah.
Like regardless of how you're splitting it. But then, just like maybe 2 or 5 minutes ago, you had also said that if you branch out, wouldn't we end up overfitting data?
Yeah. So what's interesting about using learning to build a tree is, I mean, like, okay, so the dumbest algorithm out there is like, I don't know what to call it, one nearest neighbor, we'll call it, right? Or not one nearest neighbor, well, yeah, I guess it is.
First nearest neighbor.
Yeah, whatever, right? It's that when you put your data in, you just memorize it. And actually not even nearest neighbor, like with the distance function is a binary function. Either I've seen it before, or I haven't seen it before. And if you write these arbitrarily long decision trees, you're basically encoding, I've seen this before, right? So you want to split on things that you think will generalize well. And it's just a heuristic to say small trees are better. There's no really good theoretical justification. Some people disagree with me, but like minimum description length, there's some Bayesian stuff, but it's really just a heuristic that the belief is if you have a small tree, it's just the intuition of if I can come up with a rule of thumb and it works well, it's better than writing down kind of a set of corner cases. Yeah?
So I'm just going to assume we have a decision tree on the test, and if we did have a decision tree on the test, then I would assume that it wouldn't be too long. And in that case, then we would probably be asked to go down to separate leaves where every leaf is paired. But if it was not a short decision tree, if it was like a min-length, then would we be asked to maybe know when to stop, or always go down?
So there is no right solution to a stopping criteria. The way it's done in practice, which I have in the end of the notes, is usually you just build a whole tree and then prune it after the fact. And usually you accept noise at the leaves. Like you very rarely in real life would you ever build a consistent tree. So you build a consistent tree and then you basically prune it back and allow some errors at the leaves. And actually in real life you would put a regression model of the leaf and try to prune it back, and then have some other classifiers at the leaves. But that's not yeah.
Is it safe to say that since you keep telling us that trees are used for discrete variables and logistic rules, that we would be doing a tree like this and asked to come up with a logistic rule for it?
That's a good question. But stop. I regret
I think that's a really great question.
No, that would totally be fair game.
Okay.
Is to convert a tree to rules. It makes a lot of sense. Yeah, well, it's not currently. I still can modify anything, so I shouldn't commit to anything. But that's totally a reasonable question.
Yeah.
Just convert it to rules. And we can handle real value data. It's just less convenient because you essentially have to put an implicit threshold there anyway, right? So, yeah. So these are the things that decision trees are useful for. It handles missing data really easily because you just drop it out and it tends to work okay. Because you're not explicitly representing a probability distribution. So therefore, when your data is missing, you're not making an assumption that it's missing data. You're just kind of saying, well, that's life, because you're just chopping. If you think about what decision trees are doing, if you have your space, it's chopping like vertical line and horizontal lines in your space. So you're not really explicitly making probabilistic assumptions. I mean, your entropy's close, but it's really convenient for missing data. Who cares about history? I won't ask you about history. Okay, so how do we learn them? So consistent, everything is consistent. The better solution is you want something compact. So we're going to learn our trees top down. So we just pick attribute by attribute and recurse. Finding anything that is discrete and optimal is NPR at the end of the day. So we use a greedy search in this case, where we just minimize information gain every step down. And maybe this makes more sense to you now that this is a preference bias and not a restriction bias. What I mean by that is when I say a restriction bias, that means like linearly separable. So I could learn a function that's the reason I can't, or the reason I'm making a restriction is I'm making some assumption that it's conditionally independent, that the variables, that I'm only going to be able to express linear functions, like all kinds of things like this. In this case, I can express anything, but I'm going to specify some preference for compact trees. When I do SVM, which is a linear function, well, not too far, I actually do it in both ways. That I express some specification of my functional form and some preference for which version is better, which we already saw actually in the perceptron mistake bound for margin. That margin would be a preference bias and linear function is a language bias. Okay, this is just an example where we do entropy, and I'm going to do this on the practice midterm anyway, so I don't think I need to cover this in any detail, unless someone has a specific question. Now that you're seeing this again, it's so much easier. There you go. Actually, one thing I did the homework. So yeah, in this case, we have a preference. So yeah, Occam's razor, real valued attributes, noisy data. And these are just special cases. So real valued attributes, you split on some threshold. As you see here, how do you split? It tends to be midpoints, but this is not a solved problem, so I'm not going to ask stuff like that. Okay. Let's see. Oh, so pruning, as you asked. So one way to stop is you do a chi-square test, but nobody ever does it. So what people do is they post-prune, they throw the complete tree and then prune back up. And the example I gave here was basically you had some development sets, you had some holdout data, and you just go back and compute on the holdout data and then prune those kind of noisy leaves and just prune back with them.
So that is, you just record the probability or the covering of some test data set?
Yeah, so in this case, right, so in this case here, there's some set of errors, right?
Right.
So if I was to keep it, I would have 7 errors. If I was to prune it, I'd have 4 errors. And I just go through and find all the cases and pick the one that. But this is it's an obvious thing to do. It's not like it's one of these cases. So one argument for why decision trees may come back again. Everything comes back every 20 years. They're really out of fashion right now. I think part of the reason they're really out of fashion is actually they perform well if you know what you're doing and you kind of get the art right. The issue with them is they're really poorly understood. What ends up happening is like people come up with theoretical bounds for post pruning, and it ends up that these heuristics outperform any principled method. So people like it. Performance is kind of unpredictable, where for other things it's much more predictable.
Do you
Yeah.
Are you pruning based on the training data or after like?
So